Before we get into some experimental designs to investigate different aspects of classical conditioning, it'd be a good idea to go over some of the methods or techniques that researchers use in classical conditioning experiments. So we've talked a lot about Pavlov's early work, right? He's established this method for studying conditioning in dogs because he was very familiar with the digestive system and knew how to do surgery on animals. And what he would do he would take the salivary duct out of the cheek of the animal, and it would either collect in like a test tube, like with if the animal salivated, the saliva didn't go into the mouth, it went into a little collection. Or to be more precise, the saliva would activate an electric switch that would then put a little mark right here on what is called a chymograph. And here's an electric chymograph. And what it basically is this drum goes round and round. And every time there's a little switch, a little mark is made on it. So if the animal salivates, a mark. So this is going round and round, so you can determine time because you know the circumference of this circle, and then it checks every time the animal salivates. This is a more quantifiable way of measuring saliva. But this method of the saliva creating this circuit that would activate this chymogram on a drum, it worked okay for this early research, but it's kind of messy. It's not very precise. You have to do surgery on an animal. You have to do surgery on a dog. Dogs are very expensive to keep in laboratories. So while this was great research to start the investigation of classical conditioning by Pavlov, this is rarely used today. Another method is called autoshaping. Sometimes it's called sign tracking. I'm going to use the term autoshaping. Autoshaping is used quite often in research on classical conditioning, and it's used mostly with birds. I've used this technique myself. So what happens is a bird is placed into a cage, and in the cage on one wall is what's known as a key light. A key light is simply a switch, a button that the animal can press, and there's a light behind the key light, that lights it up. So you can turn it off, you can turn it on, and you can change its color. Birds are really great because they see color really well. Most of them do. And so you can have the stimulus be different colors, red or blue or yellow. Or you can use symbols. I use symbols in a research that I did. So the key light, which means nothing to the animal at the beginning, is the CS. It turns on, and this is followed by bird pellets dropping into a little food dish. We call this a food hopper. The light comes on, food drops. The light comes on, food drops. Now, the animal does not need to press the key light, the button, in order to get food. If that was the contingency, you don't get food unless you press the key light, we would be studying instrumental conditioning. But in this case, we're just pairing the two. And what happens is the key light takes on some of the properties of the food because they are in temporal contiguity. They occur together. The UR, the unconditioned response, is pecking food. That's what you naturally do to food. So the CR, the conditioned response, is pecking the light, or the probability or the latency, how quickly they peck the light, or how often or how many times. But oftentimes it's just probability of pecking the key light. Now this is kind of odd. If the animal doesn't have to peck the key light to get the food, why is it pecking the key? Why is it pecking it? It doesn't have to do it. Why? Because it associates. It associates the key light with food. It pecks food, so it pecks the key light. And the more it pecks the key light, the greater the probability, the greater we assume the classical conditioning association. It's a very easily quantifiable method of measuring autoshaping. So here is a pigeon. Pigeons are used quite often. Here's a little key light over here. The hopper might be somewhere else. It might be that this light goes on and food is dropped over here in this corner. The key light comes on, food, key light, food, and the animal will still go over and peck the key light. This is what I did. This is a picture of my research at Oxford. I've shown this picture before. Here's a little starling. I actually just put this in there, but it would be a key light with an X on it. The X would come off, and the hopper right here, food would drop in the hopper. Key light would come on, food would drop. Key light would come on, food would drop. And the animal made the association. When this comes on, there's food, I peck the key. So this video is showing an example of autoshaping. You'll see a key light come up here, and that will be followed by the hopper lighting up and food dropping. Key light, food. We have to do that for many trials. It takes a long time to make that association. Key light, food. The animal didn't need to peck the key to get the food. They too occur in temporal contiguity. Key light, food. The animal hasn't really made that strong association yet, but these two stimuli occurred together. Key light, food. You can see the animal looking at it now, and so we're making that association. Key light, and he pecked it. And this is being recorded. He pecked it, and there's food. He didn't have to peck it to get the food. There wasn't that contingency. But you can see the mechanism of recording the activity. Peck, peck, peck. Maybe the number of pecks, the probability of pecking, that kind of a thing. Again, autoshaping is used quite often in research. Another method that's very quantifiable and very precise, this is what we're trying to do here instead of the Pavlovian work with dogs, which was great at the beginning, but kind of messy and not very precise, is we use eye blink conditioning. This is often used with rabbits. So a rabbit has actually three kind of eyelids, and one of them is this kind of clear eyelid called a nictitating membrane, or a clear membrane that covers the eye. So a very delicate light thread or string is attached to the nictitating membrane of the animal that's in a cage. A light comes on, and that's paired with a very light puff of air to the eye. The light doesn't make the animal blink at first, but if the light comes on and it's followed with an air puff to the eye, the puffing of the air makes the animal blink its eye. That's a UR. It's very natural, right? It's innate. Do this enough times, pair this enough times, and the animal will begin to show a conditioned response that's measured as probability or latency. When I use the word latency, I mean time. I mean, how long did it take to blink? And because the string is attached to the nictitating membrane and the other end of the string is attached to an automated system that records blinking, again, it can be very quantitative and very precise. Light comes on, puff of air. Light comes on, puff of air. And you measure the probability of the animal blinking when the light comes on. So here's my version of it. Excuse the animation. So here's a little string. This is attached to something that records whether the string is activated, blinking. Light comes on, puff of air, and the animal blinks. We do this trial after trial, and we can start looking at whether the animal has made that association. I will say it's very important in eye blink conditioning that the light and the air puff come really close in time. So you can't turn on the light, turn it off, wait a minute, and then puff the air. You're not going to get that conditioning. They have to either overlap, or there has to be a very, very short inner stimulus interval between the light and the puff of the air. This has been used quite a lot to look at the biology or neurology of classical conditioning, which we'll talk about in another lecture. We can do this with humans too. It's one of the few methods used for research in classical conditioning of humans. And if you look here, we're using sound. And in this one, this is all automated. The person hears a sound, and then there's a couple ways of doing this. One, an air puff, a slight little air puff in the eye. Another thing is to place just a little electrode right below the eye and add a little electric shock. When I say shock, I'm not talking, that really hurts. No, it's almost like a little vibration. And so the sound beep in the ear, and then a little vibration just below the eye, and the person will blink. And then you look to see if the sound is making them blink. And this can also be recorded with this device here. Again, a very automated way of looking at classical conditioning. Another one that I've used before when I was at the University of Hawaii, this is a method of looking at classical conditioning in insects, specifically honeybees. Now, this is called the proboscis extension reflex method, PERS. And so what would you do is you take a little honeybee and you put them in a little matchbox, you capture them, you put them in a refrigerator for just a short amount of time. It kind of cools them down and kind of relaxes them a little. And then you take them out and you kind of strap them into this little device here. Air or odor is passed across the antenna. Odor is the conditioned stimulus. This odor is not making them do anything. Follow that up with a little bit of sugar water, to the antenna or to the tongue. This tongue is called a proboscis. That's the name of it. Now, the animal will stick out its tongue, stick out its proboscis to get the sugar. And then what you do is you look at whether the odor produces the tongue response. Odor produces the tongue response because the odor is associated with sugar. Sugar makes them stick the tongue out, and now the odor does as well. And the nice thing about this is you can run a lot of animals at once. You can have a whole series of these animals in these mechanisms and run a lot of experiments once. Let's take a look at that. So here's the little honeybee. There you can see its proboscis right there. Odor is presented, and it gets a little sugar water. See it sticking its tongue out? Sticking its tongue out there. Yum, yum. Odor is off. Come back. Test the conditioned response. Blow a little odor on there. And then you can see it sticking its tongue out. Why? Because it associated the odor with the sugar water. Sugar water makes it stick its tongue out. And now the odor, which has been paired with the sugar water, also produces this proboscis reflex, or sticking its tongue out. And you can measure probability of sticking its tongue out or latency. These are all good measures. Good way of studying classical conditioning in insects. So you may have heard of this method. It's a method of looking at classical conditioning using aversive stimuli or things that are harmful. This research was done early on by behaviorist John Watson, and it's a little unethical. I mean, we can't do this kind of research now, thank goodness there. So he had a little baby Albert, and little baby Albert sees a bunny, cute little bunny. And then a loud noise is played. And little baby Albert cries. And he puts on a little pink shirt and he cries. Sorry, it's the only animation I could get. And now this little baby associates this little white rabbit with this fear, right? This aversive fear. And so now in the future, if he sees a little white rabbit, he starts crying. And in fact, he would see other things that were similar. We call this generalize or generalization. A white fur coat would make him cry. And this just showed this simple conditioning fear. This is how phobias are created. Again, not good ethics there. But it does give an example of some of the first types of conditioning using aversive stimuli. Excitatory, aversive conditioning. Excitatory meaning they associate. We talked about excitatory appetitive conditioning, associating something with something good, appetitive, food. This is conditioning using something bad, aversive, fear. And so the U.S. is often something that is produces fear, can be a little painful, like shock to the animal's foot. We don't, in research like this, we're not using shock that is extreme or severe or damaging. It's mostly just unpleasant, like a 1 amp shock. The U.S. produces fear. But fear is a difficult thing to measure, because if you do that to a rat and you give him a little shock, it'll just sort of freeze. Its muscles will freeze. It will stop doing behavior. I'm not sure if you can just look at that and go, oh, the conditioning happened. I presented a light, I shocked the little animal, and now the light makes them not move. It's not a really good measure. The CR is measured in this type of conditioning as the reduction of an established instrumental response. So here's an example. This is called condition suppression. That's the method, condition suppression. Sometimes it's called condition emotional response. It is really a commonly used technique for exploring different aspects of classical conditioning. So here's a little white rat, and it's in a little cage, and has a little lever it can press to get food, and you have a way of giving it a light or a tone, but the floor is connected. This is kind of a poor illustration, but it's connected to something that can provide shock, something unpleasant to the animal's foot. Light comes on, animal's given a shock, ouch, and it makes that connection. And you're wondering, how has it made that connection, that association between the light and the shock? The animal's just freezing. So the first thing you do is you create an instrumental response. This is not investigating classical conditioning. This is creating a response that's very known and typical. So put a rat in a little cage, presses a lever, gets food, presses lever, gets food, presses lever, gets food. It has to press the lever to get the food. That's the contingency. That's why it's instrumental conditioning. And then we know what it does. We know how much it'll press that lever. And let's say we say, well, how much is it going to press the lever to get food in a hungry rat in, 5 minutes, okay? Hungry rat, how many times will it press the lever? We've already established this. An animal already knows how to do this. And it comes in, it's hungry, presses the lever, and you say, okay, it presses the lever under good conditions. It presses the lever 50 times in 5 minutes. Good. On average, 50 times. Oh, sometimes 45, sometimes 55, but that's a pretty established baseline level. Then you might do this conditioning. You've already established the animal presses the lever, and you're wondering, how does the light, when the light comes on, what does it do to the animal's behavior? If the animal has no fear of the light, there's not been an association between light and shock. The light will come on, the animal will press the lever, light come on, it might look at it, but it's like, I don't care, and just keep pressing because it's hungry. So just the light coming on is not going to do anything. But what if you've done a few trials where the light and shock have been paired? Just a few trials. And you're wondering, has the animal made any association between the light and shock? So you put him in this cage, he's pressing the lever to get some food, and you turn the light on. And what happens is the animal goes, scared. I'm a little scared. I'm going to not press levers because I'm a little scared, but I'm hungry. And if there's not a really strong association, the animal might normally press the lever 50 times in 5 minutes. Now it's pressing in 42 or so. That its behavior was suppressed a little because it has a little fear. But what happens if the light has a really strong association with shock? It's had a lot of trials, light and shock. Well, if that animal's pressing the lever to get some food and that light comes on, it might just stop and do nothing because it's so scared. We can measure that. Okay, so in a condition suppression design, we establish an instrumental response, pressing the lever to get food. We have a record. How many times does the animal press the lever when the CS is not presented, before the CS, the baseline? right? The CS is associated with shock. What does it do when the light's not on? Or the tone, or whatever CS we're using? How many times is it pressing when it feels no fear, when it's feeling comfortable? Then, how many times does it press the lever when the CS is on? We know that number is going to be less, but it depends on the strength of the conditioning. If it's only a little scared, it's going to drop its pressing by a little bit. If it's really scared, that light really terrifies them because it has a strong association with shock, we might have a conditioned suppression of very little behavior. Then we get what's called a suppression ratio. And the suppression ratio is the number of times it presses when the CS is on, divided by when it's on plus when it's off. That gives us a ratio. Another way of saying the ratio is CS, when the CS is on, divided by when the CS is on, plus when the CS is not on, before the CS is on. Okay? So I calculated some stuff out, and we can look at changes. We can look at an acquisition function. So on trial 1, when I mean trial, I mean the light is paired with shock. That's a trial. I'm not interested in the animal pressing the lever to get food. That's instrumental conditioning. I'm interested in the light has been presented with shock. Well, on the first trial, there's very little or no conditioning at all. The light does not scare them at all. So it presses 50 times. When the light's on, and 50 times when the light's off, and 50 times when the light's on, and we get a ratio of 0.5. Just calculate. 50 divided by 50 plus 50 is 0.5. But what if we've done it twice? Light comes on, shock. Light comes on, shock. Now we've done it twice. Well, now the light is starting to make connected with the shock. So when the light's not on, it presses 50 times. But when the light comes on, we have a suppression of behavior. It went from 50 to 43. So this is 43 divided by 43 plus 50, or 0.46. It drops down. That drop from 0.5 to 0.46 is a measure of association between the light and the shock. 3 trials drops it down to 36. 4 trials, 29. 5 trials, 22. When the light comes on, it's still hungry. It's going to press the lever a little bit, but it's kind of scared because it's had 5 experiences when the light was connected to the shock. Okay? Back to my animation. That's a trial. Light comes on, gets shocked. Now we've done it 5 times, and when the light comes on, it presses it only 22 times. When the light's not on, or whatever stimulus you're using, it's comfortable. It's not scared. It presses 50 times, it's hungry. 7 times, 8, not 8 times. Now it only presses it once. 9 times, right? It's really dropped. Now, these trials, I'm just making up these trials. It might take 30, 40, 50. I'm just giving you examples, but I'm showing you that the more conditioning, the more suppression of behavior, and the condition suppression ratio decreases. So our acquisition function in this case actually shows a drop. The more association the light has with shock, the more we get a suppression of behavior. What behavior? The established instrumental response of pressing the lever. This isn't an experiment about lever pressing and does the animal learn to press levers. This is an experiment about how much the animal has associated the light with shock. This is excitatory connection, excitatory aversive conditioning. This is not inhibition. Inhibition is a signal of non-reinforcement, a signal that the shock is not coming, right? Don't confuse those two. Just because this has inhibited an instrumental response, don't confuse those two. The animal has made a connection, an excitatory connection between the light and shock. The more times we present the light together with shock, the least likely it is that the animal is going to keep pressing the lever. This is an acquisition function. Okay, finally, let's talk about something that's been done a lot. This is kind of messy. It's called conditioned taste aversion. And I imagine many of you listening to this have this in some fashion or another. In conditioned food aversion, the CS is a novel food. And in the past, I've been talking about the US being food. Ring a bell, give the animal food. Ring a bell, give the animal food. Show a light, drop some food. In this case, the CS is food. It has to be a novel food. We don't get conditioned food aversion on something people or animals eat every single day. And I imagine some of you have had this experience. I know I did. I remember one time I ate some toffee-covered peanuts at the movies. This when I was a lot younger. And I got home and I got sick. I was sick that night. And I didn't know this, but in the future, we went to movies or something. Hey, let's get some toffee-covered peanuts. I love those. I grabbed them, I put one in my mouth, and I instantly felt sick. The taste and the smell of this food had been paired with sickness. And now I don't want to eat it anymore. This is food aversion. In the experiment, the CS is a novel food you give an animal. The US is something that induces sickness naturally. What's often used in experiments is either a little bit of radiation, if we're working with rats, or lithium chloride. Lithium chloride. It just makes animals nauseous, makes them sick. Pair food with lithium chloride, and the unconditioned response to lithium chloride is feeling of sickness. So the conditioned response is measured as an animal's unwillingness to eat that food in the future, the willingness to take less food. So before we did this, the animal was happy to eat 10 little cheesy snacks for the rat. Yummy, yummy. These are novel, new foods. Oh, yum, yum. But then I give him a little bit of this cheesy snack and I make him sick. And then in the future, we find he only eats 3, right? We've had a drop of 7. That's a measure of that association. And conditioned food aversion has been talked about in a lot of ways. It's been talked about as a very specialized way of conditioning because it has such evolutionary importance. This makes sense, right? Animals going around foraging for food, eats a little berry, throws up. Hey, don't eat that food in the future. Go up to that bush, smell that food, and just go, oh, no, thank you, right? This is for the survival of the animal. And so sometimes people will say, we don't really need too much contiguity, temporal contiguity here. And in fact, I can give an animal some cheesy snack, some new snack, and I can make them sick 2 hours later. Wow, that's no temporal contiguity. And still the animal will not eat more of that cheesy snack in the future. So this seemed to violate the very important thing that Pavlov said about contiguity, temporal contiguity between the CS and the US. Others have come along and go, nah, we're not sure what's going on here. It's a mess. For example, the animal, when it's sick, it will be smelling, these highly olfactory animals will be smelling that food again. What do I mean? You know what I mean, right? Because if you've ever been sick with food, you had dinner and then you got some stomach bug or food poisoning or other, and you barf at 11 o'clock at night, you had the dinner at 6, you're tasting a lot of the similar flavors of that food. I'm sorry, that was disgusting. But it's coming up and you're tasting it. And so when you're feeling sick, you're probably experiencing some very salient odors and flavors of that food. And even though you had the food 4 hours ago, the temporal contiguity between the smell and the taste of the food and the point at which you're sick probably has temporal contiguity. Just like a rat, right? A rat, you give them a little cheesy snack, make them sick 2 hours later, it's going to smell. It's going to come up. And so this idea that conditioned food aversion violates temporal contiguity, which is paramount, so important to Pavlovian ideas of conditioning, Maybe, maybe not. This is one of those things that, like salivation, is just a really messy experiment. You don't control well timing of things. If you're really wanting to study classical conditioning and not some specialized evolution of food, you're going to use auto shaping, you're going to use condition suppression, you're going to use eye blinking, things like that.